I'm David Nuremberg, the Leon Levy Professor and Director of the Institute for Advanced Study, and it's my pleasure to invite you to this latest installment of our Director's Conversations on the place and practice of the arts and sciences in the past, present, and future of humanity. Now, so far in this series, we've discussed biography, universities, opera, museums, dance, and philosophy. In those conversations, we've focused on how important forms of human discovery emerge, persist, and change. In part, we've done this to better understand the Institute's own distinctive forms of discovery and what it can offer the future. So today's conversation is about what is still, for the moment, a human form of discovery. That's a laugh line. Though its very names, artificial intelligence, machine learning, convey that it threatens to break the category. Our questions: what are the powers of computation? How do they work? What opportunities and perils do they offer? How will they transform human knowledge and indeed humanity? Those are some of the questions, the easy ones, that we're counting on our distinguished guest, Sir Demis Hassabis, to answer for us. Now, the Institute and its faculty have been thinking about these questions for almost a century. The pioneering programmable computer that John von Neumann built here and established von Neumann architecture as the standard for computing operations well into the 21st century seemed to him just as transformative as the atomic and hydrogen bombs he also contributed to. What we are creating now, he said to his wife Clary after returning home from some bomb work at Los Alamos. This is a quote. You can usually tell the difference between von Neumann's voice and mine, or Oppenheimer's voice and mine, is a monster whose influence is going to change history, provided there is any history left. He then changed the subject to the computing machine he was conceiving at the time, and became even more agitated, according to Clary in her biography, foreseeing disaster if, quote, people could not keep pace with what they create. She had to give him a handful of sleeping pills and 2 whiskeys to calm him down. As you all know from Christopher Nolan, Robert Oppenheimer, the Institute's director from 1947 to 1966, shared von Neumann's agitation and also his affection for drink. He believed, although he favored martinis, he believed that, quote, the safety of a nation or the world cannot lie wholly or even primarily in scientific or technical prowess, but also requires attention to ethics, values, forms of political and social organization, feelings, emotions. He sought to make the Institute a place where these many forms of discovery and thought could come into contact with the goal of preserving humanity, much as we do today. The list of people he brought as part of his efforts is astounding across all disciplines. Physics, of course, but also poetry and politics and psychology, and that's just the P's. Now, not all of those disciplines are present at the Institute today. I don't think we have any full-time poets, for example. But our current faculty is just as dedicated to the task of bringing its different methodologies to bear in its exploration of the possibilities of thought and of humanity. All this is to say that Oppenheimer, von Neumann, and all of their Institute colleagues would very much wish that they could be present this evening to hear from Sir Demis Hassabis, the CEO and co-founder of Google DeepMind, 2024 Nobel Prize laureate in chemistry, and a scholar who is not only a leader of what may prove to be one of the most significant technological transformations in the history of human knowledge, but also an eloquent herald of the need to attend to the consequences of those transformations for humanity. I hesitate to plunge into Sir Demis's list of accomplishments, from his prodigious achievements as a child in chess to his co-creation as a teenager of one of the most popular and influential computer simulation games of the 1990s, Theme Park, to his influential doctoral work in the neuroscience of memory and imagination, to his founding of DeepMind in 2010 to solve the, quote, problem of intelligence with the intent upon solving it of using it to, quote, solve everything else. DeepMind's breakthroughs in artificial intelligence are justly famous, among them AlphaGo, the first program to beat the world champion at the game of Go, and AlphaFold, which cracked the 50-year grand challenge of protein structure prediction and has inspired his recent launch of a sister company, Isomorphic Labs, to propel drug discovery. But I'm not going to go further, not only because the list of achievements is so long, and for a still too brief glimpse you can look in your programs, but also because Sir Demis's biography is so astounding that you might mistake it for fiction and me for a fabulist if I continued. In fact, the writer Benjamin Labatut has already produced such a fiction. His recent novel, The Maniac, is a fictional biography of John von Neumann and his ideas, exploring how those ideas have unmoored the world. The Maniac concludes with a biography, fictional, I don't know, we can ask Sir Demis, and an account, a biography of Sir Demis entitled Brainchild, and an account of AlphaGo that depicts the powers of that program as a terrifying game over for humanity. So without further ado, please join me in welcoming Sir Demis Hassabis to the Institute stage. If I might start with the most human of topics, your biography. I've read in several places that your move into intelligence, into artificial intelligence, began with an epiphany you had as a 13-year-old when you ran out of the European Chess Championships thinking, zero-sum games are too simple, I want to work on intelligence. Is this true?
Well,
and actually,
yes.
Why don't you just tell us your entire biographical arc?
Sure.
You have.
Well, look, first of all, thank you, David, for that wonderful introduction, and it's amazing to be here. It's one of my favorite places in the world to spend time at. I think it's a unique place for many reasons. Maybe we'll discuss that later on, but I love the multidisciplinary nature of IAS, and I think it's very important, plays an important part in the world, and of course the history of it is so inspiring, and you feel that just walking around the grounds. So it's wonderful to be back here. As to how I got started in AI, it really began with games for me, actually. As with a lot of the legends here, like von Neumann, of course, and so on, started with chess, and really I started playing when I was 4 years old, and very seriously, and I was going to become a professional chess player, but really got me thinking about the process of thinking. So as when you're a kid and you're trying, playing for the England junior teams and so on, you're trying to improve your own thought processes, your own decision making. So you really end up, or at least I did, examining what goes into those thought processes, and then becoming fascinated by that. And then very shortly later, around about 8, 9 years old, the first chess computers started arriving, and when we would go to training camps with the England team, they would pull these chess computers out. And if you remember, this is sort of in the 80s now, they were physical chessboards, right? They were where you press down the key, the LED squares, and that's how you move the pieces. And of course, we were supposed to be, me and the rest of the team, we were supposed to be training on chess openings and other things. But I remember distinctly being much more fascinated by the idea that this lump of inanimate plastic, someone had programmed this to play chess at this very high level. And I actually found that more intriguing than, I guess, the chess I was supposed to be studying. And I found that fascinating. And then, with some early winnings from some chess tournaments, I bought my first home computer. In the UK, there was a big home computer hobby boom. It was ZX Spectrum and then a Commodore Amiga. And that's when I started programming. And then really my love of computers and games came together, as you say, my first professional career designing computer games and programming them. But all the games I made, like Theme Park, they had AI as the core gameplay component. So they were simulation games, usually with intelligent characters that had to react to the way the player played. And that's why some of the games I worked on became very successful, because every player had an individual experience, different experience with the game, because the game adapted to how you played it with it. Now, obviously, this is the 90s, so it's very rudimentary AI, but it already convinced me how powerful AI would be if we could scale it up and get it to the point where we see today, how incredible a tool and a technology it would be. It was obvious to me already when, I was sort of in my early teens.
You just presented games as flowing out of your biography. You began as a child, etc. And you pointed to the fact that people like John von Neumann put games at the very center of their thinking about thinking too.
Yes.
Not only in his early essay, Theory of Parlor Games, but also in the famous Theory of Games and Economic Behavior, which he wrote here with Oscar Morgenstern. So using a certain approach to games to model human behavior. What is it about these kinds of games, the zero-sum games that you abandoned at age 13, according to the Epiphany, that makes them so good, such good test cases for...
Well, look, I think if you actually, the history of AI and games has been intertwined from the very beginning, right? As you say, with the sort of founding fathers of it, like von Neumann, Claude Shannon, Turing, many of the people that have come through this place, they all actually tried their hand at writing chess computers, obviously very rudimentary ones. Very famously, Turing wrote a program, but there was no computer available at the time that could run his program, so he had to run it with his mind. And I think it took like 2 days or something to play the game. And I think the reason is because it's, you know, games are kind of microcosms of interesting parts of life. That's why we as human designers have designed those games. That's why we're fascinated by things like chess and Go and poker. They encapsulate some aspect of life in a very convenient form, one would say. So convenient and fun and challenging. So we've designed these games, we play these games because of all those reasons. But that's also why they're really well suited, I think, to AI development, because they are these microcosms of human thought, which do represent something about our culture. You know, one of my favorite books is Homo Ludens, and that really argues about, you know, the idea that in some sense we're games playing animals, right? That's what we do. I mean, we're tool making and games playing are two of the kind of traits that society and humans have. And so it's pretty fundamental, I think. And I love all games. I started with chess. I ended up playing many games because actually I think it's another way, just like language, to get to the heart of a culture. So, you know, in terms of Go, it's what they play in Japan and China and Korea. In Asia, it sort of occupies the echelon chess does in the West. And you can really get deep into what a culture really thinks about things. It's sort of embodied into their games, including the way they think about strategy, warfare. All of these things are embodied in some of the rules of these games. So it's a fascinating thing for AI then to try and for us to try and build. And then the other reason that it's convenient, why we used it at the start of DeepMind, is that you can generate as much data as you want, because you can have the system play against itself and generate effectively a lot of synthetic data which you can then learn from. And it also has very clear metrics, win conditions, maximizing the score. So that's also very useful from an AI perspective to kind of optimize against.
I never thought, I am a medieval historian, Huizinga, the author of Homo Ludens, a medievalist, and here in a conversation on AI, you get a medieval book about the Middle Ages. Homo Ludens points out, though, there are many different kinds of games. There are zero-sum games, competitive games, winner-take-all. There are also games that are just imagination games, charades. I imagine that there's a reason why it's the zero-sum games and the more rule-governed creativity games that have been so useful for the early successes of AI. Is charades a harder challenge? And if that's the case, what does it tell us about human thinking and about the relationship between computer thought and human thought?
Yeah, I mean, look, the only reason that I think zero-sum games were more useful in the early stages of AI development is the metrics are clearer than an open-ended game necessarily, right, or a cooperative game. It's usually easier to specify, you know, there's the win condition, or, you know, these kinds of things are normally easier to specify in zero-sum games. The other thing is, the other big distinction is things like perfect information games like chess versus hidden information like poker, which is harder. Of course, the real world is more like poker, it's hidden information. And I think, so we have to generalize to those, you know, the wide set of games. And I think at this point, we're able to play certainly any two-player perfect information game, but actually wider than that towards, you know, poker. There's good programs now for poker and these sorts of other more challenging games. Now, when you say charades and other things, then of course, then the system has to understand the physics of the world and visuals and become multimodal. And actually, the sorts of systems we build today, so, you know, our latest foundation models called Gemini, they were built to be multimodal from the beginning. So what that means is they don't just deal with text or mathematics or code, but also video, images, and they can understand things like intuitive physics about, you know, something going on in a video. So actually, I think think with our later systems, some of our prototype systems, we call them Project Astra, would be able to be reasonably good at something like charades now.
So I'm going to ask you a series of questions about how you pick the problems you work on, because it's quite striking. You've chosen very different problems and had such tremendous success across different kinds of problems. And you just, I think, gave part of the answer, which is benchmarks. Clear benchmarks matter. But so you almost immediately, like the day AlphaGo defeated Lee Sedol in Seoul, you started hiring biologists. For AlphaFold. So can you tell us what was it, what characteristics made that the problem you had decided to focus on?
So games was never an end in itself, right? It was a sort of means to an end. So we wanted to build, as you read out our original mission statement from DeepMind, you know, these general learning systems that could generalize and then help solve really challenging real-world problems that matter. So games were the kind of on-ramp to develop those types of general algorithms. But we were only interested in developing algorithms that not just were good at the game, but actually we thought could generalize. So there was no point building like an expert system like Deep Blue to just win at chess, because it was not generalizable to anything else. And the anything else part, what I had in mind was science specifically. Science, medicine, mathematics, advancing human knowledge with these AI systems. Going back to my childhood, you know, apart from my obsession and professional training in games, and then also loving computers, the other thing I was fascinated about was all the biggest questions. So I'd voraciously read, you know, both sci-fi but also biographies of the great scientists and books on them. Richard Feynman was one of my all-time heroes. And I'm just sort of was fascinated by, perhaps you could say obsessed by, the biggest questions, you know, and obviously, like, you know, things like the nature of reality, nature of consciousness, unified theory of physics. So physics was my favorite subject, but when I was reading some of the greats, like, you know, Feynman or Steven Weinberg, Dreams of a Final Theory, I sort of maybe took the opposite inspiration from some of those books, which was that tremendous progress had been made. Many of the people here who you know, affiliated with the Institute in maybe the 40s, the 50s, 60s, and so on. But actually, if you look later, in the 80s and 90s, had we made much progress towards this unified theory? And maybe the people would disagree with me in the audience, but I actually felt from reading Steven Weinberg's book that we sort of hadn't. It was a little bit disappointing relative to the amazing work that had been done in the early part of the century. And then I was thinking through why that is, and I was thinking, even if you were very lucky and you studied hard, and you know, maybe one could do the sorts of things that you know one could only dream about, being someone like Richard Feynman or with his genius. And even yet, there was still so much we didn't know, or we wouldn't be able to know, even with those kinds of minds working on it. So I sort of thought, well, maybe a better option would be to build a tool that could help us and help the best scientists in the world, including myself, make those discoveries. And for me, it was obvious when I started thinking through this, you know, I must have been, I don't know, 13, 14, that that would be maybe the best way to make the fastest progress towards all these big questions that the great physicists and mathematicians had been thinking about for centuries. And then additionally to that, it's a fascinating topic in itself, a fascinating intellectual pursuit in itself, the building of an intelligent artifact, the distillation of intelligence into a machine, then comparing it to another great mystery, which is the workings of the human mind and the nature of consciousness. And it also felt to me, and I did a degree in neuroscience and computer science, is that I always felt that trying to build an intelligent artifact and then being able to deconstruct that with the scientific method and comparing it to the human brain will tell us a lot about what's special or not about the human mind.
I'm going to ask a question that's maybe a little political, but AlphaFold used as its training set about 100,000 known structures in the protein structure databank. Mm-hmm. And those known structures were determined by basically one protein per dissertation by many graduate students and then scientists, mostly funded by large public investment. Think National Science Foundation, think National Institute for Health. AlphaFold has since done approximately the equivalent of 1 billion graduate student years of protein structure determination in, what, 2-3 years?
Yep.
But its initial training set was the product of that human capital investment. And I wonder, as we go up the biological complexity ladder where we don't have good training sets, beyond the genome, beyond proteins, are you worried that the kind of public investment in science necessary to create those kinds of training sets won't be in place? Or do you think that AI will be able to simulate its way to that kind of training set?
Look, it was incredibly important that we built on 50 years worth of structural biologists, painstaking experimental work to create those 150,000 roughly structures in the PDB. It actually we were only just about had enough data, because it turned out that wasn't enough on its own. The 150,000, we actually had to create an earlier version of AlphaFold that predicted, nearly 1 million structures, and then we had to triage that for the most accurate 300,000 or so, and put that back into the training set. So we actually added some synthetic data into the training, and I do worry about that. And there aren't many problems that are of that sort of importance that have that cleaner data set to work from. And that was one of the reasons I picked protein folding and had that in mind. I think you asked that question actually earlier, of because I knew I was going to work on AI my whole career, no matter what, from an early age, and then I wanted to apply it to the sciences. I've been collecting over my sort of career, when I bump into, and I love multidisciplinary environments like the IAS, and our DeepMind is one of those environments, and I've always tried to work in those kinds of environments, and not just with technologists, but also artists and designers and those things. And that's one of the great trainings computer game design does, because you work with artists, engineers, musicians, and so on all together. It's a really amazing creative endeavor at the highest level. And with the problems, you want three things that if you step back at what our systems, all our Alpha X systems do, AlphaGo, AlphaFold, and so on, the way you can generally think of them is you have some data, hopefully a lot of data, maybe you supplement it with some simulated data, some synthetic data, but you usually need some real data in order to create the simulation in the first place, and to also make sure that your simulation or your synthetic data, the distribution coming out of that, is matching to the real distribution. So otherwise, you're potentially compounding some bias or some error in your data set. So you usually need some real world data. You also need to have a clear metric. Going back to metrics, and games have clear ones, but a lot of things in science do too, if you think about it in the right way, minimizing the free energy in the system. There's all sorts of ways of thinking about metrics that you can hill climb against with a lot of natural problems. And then finally, we really like problems which can be described as massive combinatorial spaces. So generally speaking, too many options, too many possibilities to do. So brute force methods, brute force search, for example, would not work in those kinds of problem spaces. And then that makes it, if all those things hold true, that makes it really interesting for the sorts of techniques that we have, which you can think of as building a model, a neural network model of the problem space based on the data, whether that's Go or protein structures, and then using that model to guide an intelligent search process, whether that's Monte Carlo true search or, reinforcement learning, all these things, in order to tractably find the needle in the haystack solution that optimizes your metric. So that's basically it. That's what all of these systems do at their heart. But it's actually turns out it's quite a general solution to a lot of problems that can be couched in that way.
Even for math. So that's, you've turned your attention, and Google and DeepMind has turned its attention to AI for math. And in fact, much of the Google AI for Math team is here. Welcome. They've been collaborating with the Institute and with the local community of mathematics for the week, and we're very happy we're here. I guess my question is, what makes this area? You've just described the three things that make a problem interesting to you, and I'm wondering how math fits in, what makes that an interesting area, and then I might ask later, how is it different from
so if you look at some of our maths programs like AlphaProof, they basically, it's the way I think of it at least, and different people on the team think of it in different ways, but a lot of the team actually did work on things like AlphaGo and AlphaZero as well. And if you think about trying to solve a maths conjecture or something like that, one way you can think about it is that you have some equation or some formula you're trying to optimize or reduce down and find a solution to some problem. And you can adjust that formula in some way as the next step. And you can almost think about that as the next move in a game. And you have some metric you're trying to reach, or you're trying to optimize about the elegance of that, or what it can describe as your sort of guiding goal for where it's going to go to. And it feels like it's quite sort of isomorphic to the kind of things that we're able to do. And the other advantage on things like maths and coding is you can generate a lot of synthetic data because one can verify the answer. So you can actually, so that's quite useful in areas of synthetic data, is checking whether that data really is accurate that you've generated. So and that's also very similar to games and also coding, where you can verify the end position, who's won the game, or the value of the position, the different sides in the game, who's winning. These are pretty precise things that you can accurately compare your predictions against the outcome. And so maths has some of those properties too, at least some of the equations. And so, I think we are building systems now that are capable of solving pretty hard problems. We're using formal logic languages like Lean. So there's a sort of translation process. Can you convert a math problem that's maybe described in natural language into a formalized version of that problem? And then you can use the rules of that formalized logic to try to make progress.
I think many of our colleagues are in mathematics are thinking, what will the powers of AI be in math? And also, will there be areas of mathematics that remain more human and areas that are more susceptible to AI approaches? And I think that's a burning question for mathematicians, but also for all of us. And that was a year ago, you told me that if you ever got a sabbatical again, likelihood?
Probably not that likely, but we'll see.
Right. You said
maybe after AGI is done. Yeah.
If you ever got a sabbatical, you'd like to spend it at the Institute working on the P equal NP or P versus NP problem. Now, I'm not going to ask you why the Institute, because the answer to that is obvious. And I won't name check all the colleagues we have here who make it a good place for such a thing. But I did want to ask you, why P versus NP? Could you explain that problem to us, and why you find it so important?
Well, look, I think it's one of the Millennium Prize problems. It's always been the most fascinating problem to me in sort of computer science and applied mathematics, let's say. So I think it gets to the heart of computation, what is possible on classical machines. Right, sort of the P of that P equals NP, right? So the things that are, problems that you can categorize in P, what that means, it stands for polynomial, means it can actually be solved in some sort of tractable amount of time. And then the ones in NP, you can think of as they're sort of not possible, not tractable to solve in some reasonable amount of time, at least on a classical computer. And it's always fascinated me. It's increasingly become fascinating to me. So I've loved it since my undergrad. And I think it's a fundamental, core, foundational question, actually. And I think we've been investigating in our own way, because one of the things you can think of what we've done with DeepMind, and I would say my whole career, is I sort of think of ourselves as Alan Turing's champion. So, Turing and Alonzo Church and many others also affiliated here, they came up with these ideas of Turing machines, the Church thesis, all of these things that are important about what computation is, foundations of computer science, and what is possible to compute. And of course, Turing famously invented the Turing machines, and he showed that they could compute anything that was computable, and therefore anything that was could mimic a Turing machine or approximate a Turing machine was also Turing powerful. And I think what we've shown in the last 15, 20 years as a field, and also through the work we've done, is that classical methods and running on classical computers can go a lot further than perhaps we previously thought, and do things like beat the world champion at Go, or fold every protein known to science within a year. And so these are kind of pretty amazing things that would have surprised very, very smart people. I remember I'm struck with, I've had quite a few conversations with people like Roger Penrose about this. Obviously he was a big advocate of something quantum going on in the brain and quantum consciousness and things like this. And he told me he was surprised by AlphaGo as a result, right? He would not have predicted that we could create systems that could beat the best humans at Go.
Classical systems.
Yeah, classical systems. Yeah. Maybe you need a quantum system or something like that. And so I think when someone like that says that to you, who's thought about this for a long time, one has to really think through, like, when you step back again, like, what does these systems mean, having these systems? And we've had some interesting lunchtime discussions today, and that's the thing I would work on if I was here and I had the luxury of, a summer in this amazing, inspiring place to think about things, is try to make progress with what is it that we've done, and how does it affect this fundamental question about P equals NP?
Well, I have to plug the Institute. So I gave Dennis this morning a copy of the letter that Gödel wrote to von Neumann in 1956 when von Neumann was dying. And Gödel begins the letter by saying, "I hear you're getting better. I'm so happy to hear." And then he plunges right into, in a typical Institute way, a mathematical question or a question about knowledge. And he proposes, it's the first proposal of P equal or not equal NP. Unfortunately, von Neumann never wrote a response. If he had, it would be like Freiberg's last theorem. But so we will welcome you when your sabbatical comes.
Yes.
In your Nobel lecture, you proposed a conjecture yourself. I think we could have it up here.
Yeah.
Any pattern that can be generated or found in nature can be efficiently discovered and modeled by a classical learning algorithm, which grows out of what you were just saying. So what's prompted you to think about this particular conjecture, and what are its potential implications?
Yeah, I would say it's still in the formative stage. So this is an early version of it. It may change, but it's my first sort of I guess attempt at trying to categorize what these class of systems are able to do, and going back to my description of how I pick problems and why protein folding then became sort of top of the pile for me, so I came across protein folding actually as an undergrad in Cambridge in the 90s, and one of my biologist friends was obsessed with protein folding, still works on structural biology today in Cambridge, and he was always going on about it in the bars, playing table football or pool or something, and he'd be going on about how revolutionary this would be and it should be possible, and I just listened to him quite carefully as I tried to do. And I sort of realized, first of all, it would be really foundational, and it would unlock so many new branches of research, like drug discovery and so on. So it'd be a really impactful breakthrough, as well as to fundamental research. But it also struck me as the type of problem, even though we didn't have the type of AI we have today, it wasn't even invented then, that one day it felt like this incredible, like the ultimate jigsaw puzzle or something, right? Like to figure out of all the possible configurations a protein, shapes a protein could take. Some people estimated 10 to the power 300 for an average protein is the number of different shapes it could take, and that somehow in nature, spontaneously in milliseconds in your body, it folds up into this intricate 3D shape that determines its function. So it seemed like a fascinating problem, but also one maybe suited to a future sort of AI approach. So I carried that around with me for, I guess, nearly 20 years until we did AlphaGo. And then, as you said, the day after the AlphaGo, I felt we'd reached the pinnacle of games AI. That was always the holy grail, is like, can you build a system that's learning, that's general, to win at Go, the most complex game we've ever invented. And not only did it win, it also invented new strategies, new Go strategies that I'd never seen before, even though we played Go for hundreds of years. And then that, to me, was the signal that we now have enough interesting algorithms we can apply it to science, which was always the real goal, right? And then protein folding is the first big problem we tackled. So going back to this conjecture then, and taking again together the description I gave you about the model, you have some massive combinatorial problem. You can't brute force it, it's too big on a classical system. So one has to learn a model of it, and then the model, if it's accurate, will guide your search. Okay, so that's the basics of what that's the most basic way I can describe what we've done. And so then, why is this important then? Is I guess behind this conjecture is my sort of proposal is that most interesting things in nature, most natural systems, have gone through some kind of process of evolution. And I mean that very generally. I don't mean just life, but I mean it could be geological weathering, could be even cosmological, the shapes of planets and what the orbits and things like that. They've become stable over time, right? They've survived sort of spatial temporal stability. Otherwise, they wouldn't exist as entities. And that means there is some structure there that is, not random, that is not uniform, that one can perhaps learn, given enough examples. So this should probably have a caveat of given sufficient data and to a certain level of resolution. Then it might be possible to build a model of that natural system, in which case, if you're trying to find a particular state that it's in or a particular solution to some problem within that natural system, the classic needle in the haystack type of solution that you need, then these kinds of systems that I'm describing may be suitable to do that. And some of the other things that we're working on and I think could be possible are, for example, finding room temperature superconductor material, assuming that it exists in physics. One of these types of processes might be able to do that. Another example is what we're doing in drug discovery. Now we know the structure of the protein. Can you design a compound that binds to the right part of the protein, but to nothing else in the body? Because if it binds to anything else, then that's like toxicity, so you don't want that. So we're building, in our spin-out sister company, Isomorphic, we're building more AlphaFold-like technologies to do these other parts of drug discovery. And so all of those things, I think you can frame in terms of this smart, guided search through an enormous space. And, I think this, we'll see. I want to work on this conjecture, refining it and making it, perhaps making it more mathematically precise over the next few years.
Oh, so even before a sabbatical?
Yeah, well, ideally a sabbatical would help, but maybe in my spare time at 3 a.m.
I mean, one of the things that makes the conjecture so plausible is the astounding success of neural networks in addressing problems that were thought to be, from a point of computational complexity point of view, very difficult.
Yes.
Did that success surprise you? And if not, or either way, how do you account for it? And just asking for a friend, what's a neural network?
Well, yeah, we'll come back to it in a second. But I think what's surprising is, so in some ways, I'm not surprised because this was the whole point of the attempt of what we were trying to do, to build these general learning systems. Why would you even have hope that this could be possible? Yeah. Okay, so well, that's where my neuroscience background comes in, because, and again, with Turing machines. So Turing proved his proofs about Turing machines. As far as we know through neuroscience, although people like Penrose would disagree, there is nothing non-classical going on in the brain, right? At least no one's found anything. Stuart Hameroff and other big biologists have looked for quantum effects in the brain. They don't appear to be there. So our best guess, and my best guess, is that we're also classical systems, and yet we're extremely general. I mean, Turing, with his mind, came up with Turing machines and the whole theory of that. So, it's a type of, one can think of as a type of Turing machine, and yet we're able to do amazing things, including science, mathematics, chess, Go, invent all of these things, the modern world, which is pretty astounding, with our hunter-gatherer brains. I don't think we stop to think about how amazing that is enough times. I do that every time I come over on a transatlantic flight. How have we built these 747 planes with our monkey brains? It's astounding. And then you fly over Manhattan, and it's like you think back to 20,000 years ago what that would have been, and then you tell the hunter-gatherer, person, this is going to be Manhattan here in 10,000 years.
And the same brain is going to produce it.
Right, and the same brain is basically the same brain is going to deal with it.
Brain plus culture.
Extremely adaptable. Yeah, but culture is the output of our collective brains, right? It's not magic. So it's pretty astounding, and it also, I think, speaks to the extreme generality of our minds, our human minds, and so it's a really interesting problem. So the brain does this. So we know about Turing machines. So if we can mimic that, I don't know necessarily what the limit is of what is the limit. I think it's a very interesting question of what a Turing machine can actually find out. I think that's what I'd like to find out.
Well, if it's a conjecture, there may be no limit.
Well, there may be no natural limit, but of course there could be human-created abstractions. Mm-hmm. So this doesn't mean it could describe everything in mathematics or random noise or things like that, or maybe not even factorize large numbers, because there has to be a pattern or that a model can efficiently learn. Otherwise, you can't guide the search. If it's truly uniform or random, then you have no alternative but to brute force it, and then a classical system can't work.
Which is why we have cryptography, right?
Yes, but it's also what our quantum computing colleagues, they're working on, because then you would need a quantum computer.
You've been talking so far about systems you've built that are really modal. They're for AI for science. They're for a specific problem, a specific approach. But the media seem more focused on large language models and artificial general intelligence, and you're leading work on that sort of model as well. Can you talk about the differences and the challenges and opportunities you see between the modal and multimodal models?
So DeepMind started with the idea, and still continues now as Google DeepMind, we want to build AGI, right? That's the aim. This general system that can exhibit all the capabilities, cognitive capabilities humans can. And that's important because of all the things we just discussed. That's the only way. Obviously it would have massive economic value, but actually that's not the interesting thing about it from my perspective. It's more from a theoretical standpoint. That's when we would know we would have a fully general system, right? At least an approximation to it, if it can do the things the human mind can do. Because as far as we know, we're this generalized intelligence. So, that's the main aim of DeepMind, has always been. And language and general knowledge about the world is incredibly important. So we talk about it as building a world model. So we've talked about lots of model building. We started with building models of computer games like Atari games, then we built models of Go, and then we're now building models of scientific environments. But ultimately, you want a world model, so a model that can simulate things in the world and intuitive physics, how the spatial context that you're in, and break that down, and other things that object recognition, all of these things that we do effortlessly as humans. And traditionally, that's been really hard for machines to do, right? To build these kind of predictive world models. And actually, that's what I studied for my PhD, was the imagination part. So I studied memory and imagination, and showed the imagination depended on the hippocampus, just like memory. Right. And because I thought that, I was thinking of memory as a reconstructive process. It's not a videotape memory. It's reconstructed from its components. And then I thought, if that's true, then it should rely on the same brain process, imagination, which is constructing things as well from components that you've learnt, but in a novel way versus a way that you recognize, which is the purpose of memory. Should use the same processes. So we have all sorts of mental simulations and mental models in our mind, and very complicated ones, including theory of mind and theory of other people and what they're going to do in a situation, right? And that's what we do to plan all the time. Imagine you have an important business meeting or interview, next week, you're going to have a lunch with someone important. You rehearse it in your mind, like, what am I going to say? What am I going to talk about? How might it go? You can plan ahead, use this mental simulation to plan ahead. And probably that's why evolutionary it came about, because it's useful for survival and planning. And I think in the same way, we would like machines, our AI systems, to have that capability to truly be able to do now guided planning in the real world, right? And that's what you're going to need if you want something like robotics to work, or what we sometimes call universal digital assistant. So you imagine an assistant that's extremely useful in your everyday life and helps you with admin and enriches your life with recommendations. Yeah, so then you could imagine it's on your phone or on glasses, and it needs to understand, to really be a good assistant, it would need to understand the context that you're in and understand the world around you. And we're very, very close to doing that with our Project Astra program. And even very recently, we created models. Our main set of models is called Gemini, most powerful models in the world now. But we also have side projects where, like VO, there's a sort of Turing test of videos, which is a funny one that you'll find amusing if you're not in the field, which is like, can you generate a video, 10-second video of a person chopping a tomato on a chopping board? Okay, and I'm proud to say VO does it really well. But the thing that happens, if the early video ones, the tomato would spontaneously come back together, or the knife would sort of disconnect from the handle, or go through the fingers or something, and then match back in. But now our one does it perfectly. But if you actually think about that, you're generating that at a pixel level, and somehow you're keeping the consistency of slices, and they don't reform, round tomatoes, little water drops on the tomato, what a knife is. I mean, it just kind of astounds me that it can actually understand something about the intuitive physics of the world, actually just by observation. I would have said 10 years ago, it needs to act in the world. Maybe you need a robot to actually feel physics and do physics, like we do. You know, like the weight of this. What will happen if I push it over here or smash? Actually, our systems can predict that now, and very soon they'll be able to generate the image of that. It's pretty amazing if you think about what's going on.
So now I'm going to ask a question out of concern for all this progress. Sure. You speak with real fondness. You've done it already today about your experience at Cambridge, a university, and Turing and Babbage. I think you have associated Turing with Cambridge, but
yes,
forgot
I do.
Princeton.
I'm claiming him for Cambridge. Yeah.
Today, people like you working in AI are not primarily working at Cambridge or places like the Institute. You're working at Google DeepMind, or should I mention competitors?
Sure, you can.
OpenAI, Anthropic, Meta, et cetera, et cetera. So what are the reasons for that shift? And does it have consequences for the nature of the knowledge being produced?
Yeah. So I think the reason there's been a shift in that is because of, well, several things. One reason I started DeepMind, and I didn't do that in academia, was because I knew from my games background and working in games companies and starting my own games company when I was younger, that the speed at which one could get resources and also therefore make progress, you could do that faster in a company. I used to say to one of my co-founders, Shane Legg, we were both at UCL as postdocs at the time, you know, he wanted to do it in academia. But I said that it's gonna, you know, we'll be like 50, actually, sadly the age I'm sort of at now, before they give us any resources to, you know, to actually pursue this, right? This is when we were in our late 20s and early 30s. And I thought, like, we can accelerate it 10x. So one is speed, you know, not having to deal with bureaucracy and other things when you're a startup. Obviously, big companies also have their own bureaucracy, so you have to overcome that. But the main reason is it's turned out the way AI has gone is it needs a lot of resources, mostly compute. It's not really data, actually, because we're mostly using the open web, which everyone can access, but it's just compute power for the way that the scaling has gone, and it's become quite engineering heavy. Having said that, what I suggest to my colleagues in academia, and we talked about this earlier, is there are many things that academia should be doing orthogonal to that. So don't try and build, you know, places like us, we're spending billions of dollars to build the machines to then, with amazing engineers, world-class engineers and research, to build these Gemini foundation, you know, top foundation models. But they're available for pennies on the dollar, to, you know, for anyone to run. There's actually very good open source models. So you could do a lot of experiments very cheaply with the models, but to go further in terms of like understanding what they do, interpreting what they do, maybe building benchmarks to constrain the behavior of it. We're in desperate need as a field, and I think as the world, for better understanding these models. Now, of course, companies are doing this too. We have very smart divisions and groups working on this, but we're also building the models, and that is the main track of what industry is doing. So I think academia, civil society should be figuring out what happens next in a way, not chasing after what the companies are already doing. Just utilize all those billions of dollars of basically R&D, take advantage of it, and then move into these other domains, and including, and I think this is perfect for the IAS, areas of philosophy, economics, sort of multidisciplinary, what's going to happen to the future of you know, the human condition, you know, purpose, the economic benefits, how do we spread that you know, fairly, and then the risk inherent in the technology itself. You know, how do we test for traits that we don't want? For example, like deception. It'd be pretty terrible if our AI systems had that capability. How do we test for it? How do we get rid of it? And how do we keep?
You're trying to teach them to play poker.
Well, sure. I mean, exactly. So poker, you know, and maybe that's a good test case for seeing, you know, what does this look like? You know, I always keep telling some of my neuroscience colleagues, you should be doing all the amazing things we've invented the last 20, 30 years in neuroscience and cognitive neuroscience and systems neuroscience. We should bring to bear on these artificial minds. You know, what's the equivalent of single cell recording or fMRI on an artificial mind, right? So in theory, we should be able to understand even more than we do about the human mind with these artificial minds, because not only can you ask them things and they can answer back in natural language like each other we can do, but you could do that at the same time as looking at every neuron in its artificial mind. So I think there's a lot of revolutionary work to be done there, probably cross-disciplinary, and I think that would be very well suited to the academic environment. And in some ways, it'd be better if academia did that, because if industry did it, say benchmarking, and we are doing it, it's a bit like marking your own homework. I think it'd be better for society if it's academia or safety institutes or something independent that's actually looking and analyzing at what industry is building.
Yeah, I bet you theory of computing and complexity theory has a lot to offer too from academia. We had here Shafi Goldwasser the other day speaking about how the adversarial models of cryptography can be applied to do validity testing for AI and these kinds of things. So I see lots of possibilities even for the non-engineering disciplines. You recently received the Nobel Prize. Jennifer Doudna, who had won the Nobel Prize earlier for her breakthroughs in gene editing, said that you were building tools that don't just help us understand life, but help us shape it wisely. And I want to focus on the wisely part. As you create these technologies with the power to reshape life, how do you think about the risks and the dangers, and how do you protect against them? Maybe if you want to offer an example of a tool and how you think about it.
So we thought about this for a very, very long time, because even when we were starting DeepMind, even before that, we had this very ambitious mission in mind, and we actually planned for success. Even though, if you wind your mind back to 2010, nobody in industry you could barely get any money for starting the company. No one in academia a very small pockets of academia were working on this. People like Jeff Hinton. So it was really nascent, and no one really thought it would be successful. I remember a lot of discussions I had at MIT with, I actually did my postdoc at MIT, but I spent it with Tommaso Poggio in the neuroscience building, partly because I knew I would not be welcome in the AI building, which is pretty funny if you think about it, because CSAIL is the most famous AI lab probably in academia. But it was really the bastion of, it may still be, but of traditional sort of logical approaches to AI, right? With Chomsky and Patrick Winston and so on. And
Chomsky was here too, by the way.
Yes. And there were a lot of people, a lot of people were objecting there to the idea of learning systems and general systems. It's really kind of like the opposite way to think about it than the expert system approach. But we've been planning for success from then. Like, what if we're right, and what if we're successful, and it really is as influential and as impactful as we hope? You really could apply it to many areas of science and medicine. So that's all the positive use cases. Maybe one day we'll be able to cure almost all diseases with the help of AI. I think that might be possible. And incredible things, help with climate, find new energy sources. We work on fusion with collaborators on fusion to try and use AI systems to contain the plasma in a tokamak. Material design, all of these amazing things we're working on. Climate prediction, weather models. So that's all of the amazing things I think that AI is going to bring to society. But something that transformative and general purpose obviously comes with attendant risks. It's a dual-purpose technology at its heart. And there's two big things I've always worried about, and I still worry about. One is bad actors, whether it's individuals or rogue nations, repurposing these general-purpose technologies that were meant for good, medicine and so on, but for harmful ends, right? That is possible. And then secondly, the second big worry I have is inherent risk in the AI itself as it becomes more autonomous, more agentic. So the next era is going to be agents which are able to accomplish things more autonomously, a bit more like our games programs, but they were agents like AlphaGo, but more generalized, right? Not just playing a game, but with world models and so on. And then as we get towards AGI itself, how can we control those systems, put the right guardrails around those systems, understand them well, what should we deploy them for, and how can we keep control of that technology. And so those are two really big challenges. One set of challenges is the technical challenges. I'm actually pretty optimistic about those if we give ourselves enough time as humanity, as a society, to carefully approach that tipping point of AGI. I would advocate doing it in a sort of collaborative, scientific way, a model a little bit like CERN, but it's not the current way the world's going. So that's going to be tricky in itself, but I actually think the bad actor issue and what you want to do is give access to these systems to good actors to use for science and all of those things, but how at the same time do you restrict that, what's inherently a digital technology, to the bad actors? And I think that's going to be difficult without international cooperation, which may end up being the harder challenge in today's geopolitical world.
Well, my last question was going to be, I was going to draw, I can't now, he just answered it, an analogy with Robert Oppenheimer, whose first act was Los Alamos, and whose second act spent here was trying to create the conditions of possibility for humanity to survive technology. And really the question is, and I think in my introduction I mentioned that that's not a question just for science and technology, and I was going to ask you, what are the most important non-technological steps you think our societies should be taking as we develop this technology?
Well, I mean, I've read a lot about Oppenheimer and the Manhattan Project, and so many great books written about that, and we've got to try to learn the lessons from that as those of us coming later with, equally transformative technology. And it's so prescient of von Neumann to say that in your introduction, right? It's amazing that he thought of that back then, that computation could be even bigger than nuclear. And I think he's probably right. And I think we need new institutions. So I was actually discussing it with some of the other Nobel winners in the ceremony in Sweden. The economists that won it this year are all experts in institutions and the power of institutions if you build them right. And I sort of said to them, maybe you should spend some time on thinking through what we need for AI. I've already mentioned international CERN type thing. CERN's not exactly the right model, but it would need to be a new thing. But you also maybe need the equivalent of the IAEA, atomic agency, to sort of monitor rogue projects, dangerous projects that are, with designs that are unsafe. And then on top of that, ideally, you would have some kind of governance body that's a wise council that represents the world. Some sort of technical UN is how I describe it. But, the UN itself doesn't seem that functional at the moment. So, it's going to be a tricky one. But
on this, they got it right, because they recruited our own Alondra Nelson to help advise them on their AI policy.
Yes.
And so on that last plug for the Institute, we're working on this problem too. Thank you, Dennis.
Thanks very much. Thank you.